Let us look at this example 5. So we're kind of stepping it up. So far I have shown you many different examples on evaluating the derivative of the ln or log functions. Guys, here we have a combination of many things going on here. So let us look at this particular example. So we have a quotient of two functions, right? So that already tells me like we may have to use the basic property of the quotient rule for the logs, right? That's fine. And then we still have these things, it's raised to the power 2. It also means like we may have to use some other basic properties of the logs. But guys, first thing first, it is the quotient of 2. So we should first start by actually breaking it down using the basic property of the quotient rule for logs, which says if you have a log of a ratio of two functions, like of the form log of m over n, which is equivalent to log of m minus log of n. And again, the reason why we are actually using the properties is to make life a little easier or simpler for us, so that it becomes easier for us to find the derivative of this function. Guys, if we directly start using the chain rule on this, it's going to be a little complicated, right? So let us start by using the first property. Using the first property, this is going to be equivalent to ln of, so it's ln of x plus 1 whole square minus, I'm using the basic property of the logs, which is also called the quotient property for the logs, minus ln of this whole thing in the denominator, 3x minus 4 whole cubes times x minus 9, right? X minus 9. Guys, that is my first step. I have to use the quotient rule first. I cannot use any other base property of the logs right away. First, we have to use the quotient rule. Now let us analyze this each piece. Guys, this first piece, again, we can use a property which is called the power property of the logs. Using the power property, because this is of the form ln of x to the power n, right? Or m to the power n. So what do you do with the power? You bring that up front, you multiply by that. So using that, this can be written as 2 times ln of x plus 1. All we are doing is we are trying to use the properties of logs so that it becomes easier for us to evaluate the derivative. Then guys, the next one I'm going to start with the parentheses. Guys, looking at this guy, it is a product of two functions. So again, we have a property which tells us how to deal with the product of the two functions when we are taking the log of the product, right? Log of the product, we use the product property, the basic product property for the logs, which tells me if I have log of m times n, it is equal to the log of m plus log of n. So we're going to break it into two pieces, and it's going to be ln of 3x minus 4 whole cubes plus, right? With the product property, it's the plus. But guys, I have to put this in parentheses because now I have two terms. I have binomials, I have two terms, so we got to always put them in parentheses so that when we distribute this negative, we don't forget to distribute it with both the terms. And then the second term is going to be ln of x minus 9. So guys, we are not applying or doing any derivatives yet. We are just using the basic properties to simplify this expression. Once we simplify, or we're exhausted with using all the properties, then we will start using the rules for the derivatives. Now let us look at this each individual piece. This is already simplified. We cannot do any further as far as the properties of logs is concerned. Guys, this is totally simplified. This can be simplified again using the power property. You just have to simply bring the 3 up front. So let me first do that, and then I will start applying the derivative. So at the same time, I'm going to distribute this negative. So it's going to be minus 3 ln of 3x minus 4, right? And then I also have to distribute this negative here. So it's going to be minus ln of x minus 9, right? So I think we are done with using the properties. Now let us go ahead and start applying the derivative rules. So applying the derivative rules, guys, this is just going to be 2 over x plus 1, because the derivative of this function is just 1 over the inverse function, although we still have to multiply by the derivative of the inner. In this case, the derivative of the inner is just 1. I'm going to write it, but it's not going to really change anything here. Guys, then moving on to the next one, this 3 over, again, the inverse 3x minus 4 goes in the denominator, but we have to multiply by the derivative of the inner, that is the chain rule. Well, in this case, it is going to matter because the derivative of the inner is 3, so we got to multiply by 3, and that's going to actually change this. 3 times 3 in the next step is going to be 9. And then, guys, the last one is just 1 over x minus 9, and you got to multiply by the derivative of the inner again, which is just simply 1. So let us go ahead and simplify things. It's 2 over x plus 1. Right, and then this would be 3 times 3 is 9 over 3x minus 4, and the last term is minus 1 over x minus 9. Guys, I'm going to leave it like this. If you want to if you are expected in your test or in your homeworks or wherever you are trying to do it, if you are expected to like combine these terms, like combine numerators, then you know you have to create common denominators. That is some extra work, but I hope you can already do that on your own. But if you leave it like this, that is totally correct. You can leave it like that. So guys, this is how you deal with the complex log of a complex function like this. You again rely heavily on the basic properties of the logs. You use all those properties, as many as you can. Like in this case, we used all three of them. We used the quotient, we used the product, we used the power. And then once we have it in three different pieces, then it was very easy for us to actually write or find the derivative of each individual piece. Once we have it, we have the final answer. Okay, so guys, this is example 5. I will see you next time with more examples. Till then, take care.